In this video, we're going to look at trig equations. So we're just going to be solving equations, but those equations have trig functions as part of them. The first thing you're going to do is treat the trig function like your variable. We want to isolate the trig function. So in this first problem, I'm going to isolate sine x. So I'm going to go through the process of solving an equation like we normally would. I'm going to add 1. So I would get 2 sine x equals 1. And then I'm going to divide by 2. And I get sine x equals 1/2. Once you isolate that trig function, we want to look for the angles that have a sine of 1/2. Now, this is not quite the same as doing inverse trig. So, in previous videos, if you've watched those inverse trig, I'm only going to get one value for my answer. However, when I'm solving a trig equation, we're solving for x. So we're saying the sine of some angle can be 1/2. I want to list all the angles that have a sine value of 1/2. Okay, so instead of thinking of it in the inverse trig way, I'm just going to get to this point and I'm going to say, all right, at this point, I'm going to look at my trig chart. I'm going to go down the sine column, and I'm going to look for 1/2, and I'm going to write those answers in. So where is sine 1/2? That happens at pi over 6. Keep going. It also happens at 5 pi over 6. Okay, that is where sine is positive 1/2. Pi over 6 and 5 pi over 6. So I'm going to say x can equal pi over 6 and x can equal 5 pi over 6. Now, those are the two angles on the unit circle where sine is 1/2. But as you remember, hopefully, when you introduce angles larger than 360 degrees, or 2 pi, you just keep going around the circle and you keep getting the same values over and over and over again. Which means I want to not only list the ones that are on the unit circle, but I want to incorporate my answers to give me all of those angles where sine is 1/2. So the way we do that is we say whatever our value is on the unit circle plus 2k pi. And what that says is plus any multiple of 2 pi. So any coterminal angle to pi over 6 would also have a sine of 1/2. And the same is true for 5 pi over 6. If I keep going around the circle and keep getting coterminal angles to those values, I'm going to keep getting sine angles whose sine is 1/2. Okay? So that is my complete list of solutions. All right. Number 2, tangent squared of x equals 3. So I'm going to add 3. So I have tangent squared of x equals 3. Then I'm going to take the square root, and that would give me that the tangent of x would be positive or negative the square root of 3. So what I want to look for here is I'm going to go down my trig chart for tangent, and I'm looking for places where tangent is positive or negative the square root of 3. So that happens at pi over 3, at 2 pi over 3, at 4 pi over 3, and at 5 pi over 3. All 4 of those angles, I get a tangent value of either positive or negative the square root of 3. So I'm going to list all those out. Those were all of our over 3's. So x equals pi over 3 plus 2k pi. X equals 2 pi over 3 plus 2k pi. Run into this other problem, but that's okay. X equals 4 pi over 3 plus 2k pi. And x equals 5 pi over 3 plus 2k pi. Now, one thing that you can do is you can try to condense your answers. So instead of listing all of those out, I want to think about where these answers are located on the unit circle. So what I'm saying is my answer is every single one of those angles plus a full rotation. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. All of those plus full rotations. Well, what I want you to notice is that pi over 3 and 4 pi over 3 are a full half rotation away, right? If I just go half a rotation of the circle from pi over 3, I get to 4 pi over 3. And likewise, 2 pi over 3 and 5 pi over 3 are exactly right across the circle from one another. So that's a half rotation of the circle there. So what I can say is, instead of saying both the pi over 3 and the 4 pi over 3, I could just say pi over 3 plus a half rotation, which would be k pi, not 2k pi, and then I don't have to list both of those. And I could do the same thing with 2 pi over 3 and 5 pi over 3. I could just say 2 pi over 3 plus a half rotation, and that takes care of that 5 pi over 3. And now this is my condensed answer. Okay, so you could try to do that. It makes your answers look a little bit nicer. But I would always be on the lookout for that every time you write your answers in. Is there a better way, a more condensed way to write those answers? Okay, number 3. Solve the equation 2 cosine squared x minus 7 cosine x plus 3. So again, I want to think about how I would solve this if this were an algebraic equation, and I want to do the same thing. And what I'm noticing here is that I have two different cosine functions. One of them is squared and one of them is not. So this is kind of the form 2x squared minus 7x plus 3 equals 0. It's a quadratic form equation. So I'm going to solve it as such. Okay? Pretend like that is just a quadratic function. How would I factor that? Well, I would have 2 cosine x and cosine x as my lead terms in my factors. My last two terms have to multiply to 3, so I know one of them is going to be a 1 and the other one's going to be a 3, and they have to add to negative 7. So I'm going to make this the minus 3, and I'm going to make this the minus 1. And if you FOIL that out, you'll get the 2 cosine squared x minus 7 cosine x plus 3, right? So 2 cosine squared x minus 6 cosine x minus 1 cosine x, that's going to give me the minus 7 cosine x, and then plus 3. At that point, I can set each one of these equal to 0. So 2 cosine x minus 1 equals 0 is going to give me cosine x equals 1/2. And this one would give me cosine x equals 3. Alright, so I want to look at my trig chart and find every place where cosine is 1/2 or where cosine is 3. Well, cosine is never 3 because 3 is not in my range of values that I'm allowed to get. So this one has no solution to it. I can't solve that. I'm just going to ignore it. I'm going to look for where cosine is 1/2. Cosine is 1/2 at pi over 3 and also at 5 pi over 3. So x equals pi over 3 plus 2k pi, and x equals 5 pi over 3 plus 2k pi. Those two values are not halfway across the circle from each other, so I can't condense that. That's my final answer. Okay, next up we're going to actually use an identity to solve this, and the identity we're going to use is double angle. We have sine of 2x. Sine of 2x. Well, I don't like to have numbers in there with my x. So if I use my double angle formula, sine 2x is 2 sine x cosine x. So I'm going to replace this with 2 sine x cosine x. I'm going to keep the rest of it the same. Minus cosine x equals 0. Then I'm going to factor out a cosine x. Both of those terms have a cosine x. And that would leave me with 2 sine x minus 1 equals 0. And now I've essentially done what we did in the last problem. I have factored it into a product, and I can set each one of those equal to 0. So I can say, hey, this is going to be 0 when cosine is 0, or when 2 sine x minus 1 equals 0, which means where sine x is equal to 1/2 if I add 2 and add 1 and divide by 2. So now I'm looking for all the angles where cosine is 0, and also where sine is 1/2. Well, we already got the sine being 1/2 part. We did that here. So I know that these two answers are going to be solutions. I'll go ahead and say those. So x equals pi over 6 plus 2k pi, and x equals 5 pi over 6 plus 2k pi. I also need to look for where cosine is 0. So where is cosine 0? That happens at pi over 2, and again at 3 pi over 2. Okay, so pi over 2 and 3 pi over 2. So x equals pi over 2 plus 2k pi. X equals 3 pi over 2 plus 2k pi. We don't want to be redundant. These two angles are halfway across the circle from each other, pi over 2 and 3 pi over 2. Those are exactly halfway across. So I could just say pi over 2 plus k pi, and I can get rid of that. So my answers, pi over 6 plus 2k pi, 5 pi over 6 plus 2k pi, and pi over 2 plus k pi. All of that would be all my solution set to that equation. Okay, last one. So here we want to solve this equation, but we want to specifically find all the solutions on the interval from 0 to 2 pi. So what does that mean? That means I don't want to list out just my generic, hey, this angle plus 2k pi, because that gives me an infinite set of solutions. I only want the ones on the unit circles, or on the unit circle, 0 to 2 pi. Okay? So I'm going to go ahead and start solving this. I'm going to add 1, divide by 2. Same as what I've done for all these other ones. So sine of 3x is equal to 1/2 when I add that 1 and divide by the 2. Now the mistake here is people will divide by this 3. And you can't do that because it's inside your sine function. I don't have an identity for triple angles, right? Sine of 3x. I don't know what to do with that. So I can't use an identity like I just did on the last problem. So how on earth are we going to deal with this? Well, the idea is that I can go ahead and just say, instead of x equals, I can say 3x equals. 3x equals, where is sine 1/2? Well, we already determined that a couple of times. It's at pi over 6 plus 2k pi, and also at 5 pi over 6 plus 2k pi. Now, I haven't solved for x yet. I said 3x equals those things. So now I can divide by 3, and I'm going to divide all of this by 3. Same thing here. I'm going to divide all this by 3. And now I have that x equals pi over 6 divided by 3 is pi over 18 plus, and this is just going to look kind of weird, it's going to be 2/3 k pi. Right? I got to divide the 2 by the 3 there, so 2/3 k pi. And I have x equals 5 pi over 18 plus 2/3 k pi. Now, we've written the generic solutions. I only want the ones that are in between 0 and 2 pi. Those two answers I have, pi over 18 and 5 pi over 18, are in between 0 and 2 pi. They're both smaller than 2 pi and they're positive. So how do I figure out the rest of them? Well, when I'm adding this 2/3 k pi, I want to think of it as, I want to get a common denominator so I know what I'm adding to my numerator, right? So if I multiply that by 6, that's going to be to say, hey, add 12 over 18. Add 12 over 18. That's 2/3, multiply the top and bottom by 6, so I get a common denominator. So add multiples of 12 to your numerator. All right, well, if I did that, and this would be the same thing, right? Exact same thing. So I'm adding 12 over 18. So if I go to list out all my solutions, the two smallest angles that are solutions are the ones that we found. Pi over 18 and 5 pi over 18. Now with each one of those, to get my next one, I'm supposed to be adding 12 over 18. That's 2/3 with a common denominator 18 there. So if I take this 1 over 18 and I add 12, I'm going to get 13 over 18. If I take my 5 and I add 12, I'm going to get 17 over 18. Okay, well, those are still less than 2, and how do I know that? How do I know that? Well, if my denominator is 18, I want to think about 2 as being twice 18. I want to think of this as 36 pi over 18. I don't want to go beyond that. If I go beyond that, I'm bigger than 2. Right? So far, we haven't gone above that. 17 is the biggest one we have on top. So I'm going to keep adding 12 to my numerators. So I'm kind of doing every other one here, but I'm going to add 12 to 13. It's going to give me 25 pi over 18. And I'm going to add 12 to 17. That's going to give me 29 pi over 18. The next one would be, hey, add 12 to 25. Well, if I do that, I get 37 pi over 18. Uh-oh. That's too big, right? That's bigger than 2. 37 over 18 is bigger than 2 because 36 over 18 is 2. So that's too big. So all of my answers that would be on the unit circle. Now, clearly they're not unit circle angles, but they are, I could put them on the unit circle because they are less than 2 pi, are all of the angles in that list. Okay, those are my solutions. So that's how you handle that. If you have, if you're asked to find all the solutions on that interval from 0 to 2 pi, you want to make sure that you don't exceed 2 pi, and you also don't want to write your generic answers, but you need to do that in order to get that list of solutions.